Light exerts pressure. It is a mechanical force. You cannot feel it on your skin, yet at the absolute extremes of the cosmos, the momentum of light is the only thing stopping a dying star from collapsing into a black hole. But in a small, irradiated pocket of deep space, something is ignoring the rules of light and gravity entirely. We have found an object so impossibly heavy that its own radiation should have blown it to pieces the moment it was born, and yet it is still burning. Physicists call it the Eddington Limit. It is a hard mathematical wall. This limit dictates exactly how large a star is allowed to grow before the outward force of its light overpowers the inward pull of its gravity. If a star gets too massive, the energy escaping its core becomes a hurricane of radiation, pushing against the very gas trying to fall onto it. The universe enforces a strict weight limit on stellar objects. The math tells us that no star can form beyond 150 times the mass of our Sun. But the universe is hiding a flaw in its own machinery. To see the violation of this law, you have to look outside our galaxy. 160,000 light-years away, drifting in the satellite galaxy known as the Large Magellanic Cloud, sits a vast, turbulent complex of dust and ionized gas. The Tarantula Nebula. It is a violent theater of creation where gravity crushes clouds of raw hydrogen into new suns. The conditions here are unforgiving. The distances are agonizing. If you were standing at the edge of this nebula, light itself would take 1,000 years just to reach the other side. Deep inside the densest core of this nebula, bathed in lethal ultraviolet radiation, lies a crowded cluster of stars known as R136. It is a chaotic neighborhood, but one object in this cluster dwarfs everything else. The star R136A1. When astronomers first measured its light, they assumed their instruments were blending the signatures of several different stars together. The numbers coming back were grotesque. The data did not just bend the Eddington limit, it shattered it. The light spectrum revealed a single solitary star burning with the mass of more than 300 suns. Try to visualize what that means. Our Sun contains over 99% of all the mass in our entire solar system. Every planet, every asteroid, every ocean, and every piece of iron on Earth is just an afterthought of dust compared to the Sun. Now take that immense mass and multiply it by 300, cram it into a single sphere, and ignite it. The paradox is not merely that it exists. The paradox is that it is physically impossible for it to have formed. Stars are built by accretion. Gravity pulls cold gas inward, but as a young star gets larger, it gets exponentially hotter. By the time it approaches the theoretical limit, the light it emits is so intensely violent that it literally blows the surrounding gas away. It starves itself. The mechanism of its birth should trigger its immediate destruction. There is no known process in standard astrophysics that allows a star to quietly gather 300 solar masses of material. It sits there in the dark, pouring out nearly 9 million times more energy than our Sun, burning its own fuel at a terrifying rate. It is a titan that breaks the fundamental physics of stellar evolution. It should not be there. But the telescope data is absolute. We are looking directly at a physical impossibility. And the only way it can exist is if our understanding of the universe is deeply, perhaps dangerously incomplete. To understand why a 300 solar mass star is an anomaly, we must first abandon a deeply ingrained human intuition. When you stand outside on a clear day, you feel the warmth of the sun on your skin. You see the glare. You intuitively understand light as a visual phenomenon, a wave of heat, an abstract form of energy. But your intuition is hiding the physical reality of the universe. Light is not just brightness. Light has momentum. It exerts a physical, mechanical force. It can push. Physicists call this radiation pressure. To understand it, you have to look at light on a particle level. A photon carries no mass, but it does carry momentum. When a photon strikes an atom, it transfers that momentum. It delivers a physical kick. On Earth, this force is so incredibly weak that it goes entirely unnoticed. The gravity of our planet anchors you, and the atmospheric pressure wraps around you. The pressure of sunlight hitting your body is less than the weight of a single grain of sand. You walk through it as if it were nothing. But the physics of the cosmos do not operate on a human scale. If you increase the amount of light to extreme apocalyptic levels, that gentle push transforms into a kinetic wall. It becomes a force capable of shredding planets and dismantling stars. A star is not a solid object. It is a continuous, violent war between two opposing forces. On one side, there is gravity. Gravity is relentless. It wants to crush everything down to a single mathematical point. A star is born because a massive cloud of hydrogen gas collapses under its own staggering weight. As millions of trillions of tons of gas fall inward, the pressure at the core becomes unimaginably intense. The temperature spikes. Atoms are violently stripped of their electrons. Nuclei slam into one another, and nuclear fusion begins. This is the ignition. This is where the second force joins the war. The fusion of hydrogen into helium releases a torrential flood of photons. These photons want to escape into the vacuum of space, but they cannot travel in a straight line. The interior of a star is so dense that a photon is immediately absorbed and re-emitted by the surrounding plasma millions of times. It fights its way toward the surface, and every time a photon strikes an atom, it pushes outward. For a star to remain stable, these two forces must achieve a perfect, terrifying stalemate. The crushing weight of gravity falling inward must be exactly cancelled out by the kinetic force of light pushing outward. Physicists call this hydrostatic equilibrium. It is the only reason the sun in our sky does not collapse in on itself or explode into a supernova. In the early 20th century, a British astrophysicist named Arthur Eddington began to decode the mathematics of this balance. He realized that this equilibrium comes with a strict, unbreakable ceiling. Eddington looked at the relationship between a star's mass and its brightness. The math revealed a brutal reality. The larger a star becomes, the more gravity it has. To fight off that increased gravity and prevent a collapse, the core must burn its fuel faster. But the relationship is not simple. If you double the mass of a star, you do not simply double its brightness. The core gets so heavily compressed that fusion accelerates exponentially. A star twice as massive as our sun is not twice as bright. It is roughly 10 times brighter. If you increase the mass to 10 times that of our sun, the star becomes thousands of times brighter. The light output scales violently. This is where the architecture of stellar physics begins to break down. As you keep adding mass to a star, the gravity increases, but the outward force of light increases much, much faster. Eventually, you reach a critical threshold, a mathematical breaking point. At around 150 times the mass of our sun, the fusion reaction in the core is so ferocious that the light pushing outward literally overpowers the gravity pulling inward. The radiation pressure becomes greater than the gravitational binding energy holding the star together. If a star were to somehow grow beyond this point, its own light would physically tear its outer layers apart and blast them into the vacuum of space. This is the Eddington Limit. It is not a mere suggestion of nature. It is a physical barricade dictated by the inverse square law and the behavior of subatomic particles. Knowing this limit, astronomers must confront the horrifying reality of stellar birth. Stars do not just pop into existence fully formed. They grow, they feed. They begin as dense knots inside vast molecular clouds, gathering material from a spinning disk of gas and dust. This process is called accretion. Gravity acts as the engine, dragging cold hydrogen inward. For accretion to work, the gas must be incredibly cold, just a few degrees above absolute zero. If the gas is warm, the thermal energy makes the atoms vibrate and resist the pull of gravity. The cold allows the collapse. But accretion has a fundamental, unavoidable flaw. As the young star feeds and grows more massive, its core ignites. It starts producing radiation. The larger it gets, the brighter it burns. By the time a developing star reaches 30 or 40 solar masses, the light it shines into the surrounding cloud is blinding. The radiation pressure begins to hit the incoming gas. Because the gas cloud contains traces of heavier elements like carbon and iron, it is not perfectly transparent. These heavy atoms act like nets catching the outbound photons. The photons transfer their momentum to the atoms, pushing the gas away. As the star approaches 100 solar masses, the outward pressure of its light is so intense that it halts the accretion process entirely. It pushes the surrounding gas cloud back into deep space. The star effectively destroys its own food supply. The physics of accretion dictate that a star will naturally isolate itself long before it ever approaches the Eddington limit. The mechanics of its birth prevent it from reaching critical mass. This is why the vast majority of stars in the universe are small, dim red dwarfs. Massive stars are incredibly rare because the universe actively prevents them from feeding, and this brings us back to the monster in the Tarantula Nebula. R136a1 does not just sit near the Eddington limit. It is double the theoretical maximum, over 300 times the mass of the Sun. How did a star gather that much material when its own radiation should have completely vaporized its accretion disk when it was only a fraction of its current size? The mathematical models break down entirely. We are forced to look at a system that ignores the established rules of gravity, thermodynamics, and radiation. To maintain this impossible mass, R136a1 exists in a state of continuous, violent destruction. It is burning with a luminosity nearly 9 million times greater than our Sun. The surface temperature is over 45,000 degrees Celsius, which is 8 times hotter than the surface of our Sun. At these extreme temperatures, the star is not primarily emitting visible light. The vast majority of its power is pouring out in the form of extreme ultraviolet radiation and X-rays. If you were placed anywhere near this star, the radiation would strip the flesh from your bones on a molecular level before your nervous system could even register the damage. But the most disturbing aspect of R136a1 is not its heat, it is its wind. Because this star is violating the Eddington limit, gravity is losing the war. The radiation pressure is so overwhelming that it physically drives the outer atmosphere of the star away at velocities exceeding 2,000 kilometers per second. That is a solar wind traveling at nearly 6 million miles per hour. The sheer volume of material being ejected is staggering. Our Sun loses a microscopic fraction of its mass to solar wind over its entire lifetime. R136a1 is shedding the equivalent mass of the entire Earth every few days. It is bleeding into the void at a catastrophic rate. We know that stars this massive consume their fuel with terrifying speed. A small star can burn quietly for trillions of years. Our Sun will live for about 10 billion years. But a star carrying 300 solar masses is burning so violently that its entire lifespan is compressed into a kinetic flash. R136a1 will likely only live for about 2 to 3 million years. On a cosmic timescale, that is not a lifespan. That is a brief, violent detonation. This creates a severe problem with time. Because it lives for such a short time, the window in which we can observe it is incredibly narrow. We are looking at a star that is essentially a cosmic ghost. By the time the light from R136a1 traveled the 160,000 light-years to reach our telescopes, the star itself had already evolved. We are seeing it as it was deep in human prehistory. But even looking at it in the past, the core problem remains. We are looking at a snapshot of a structure that the laws of physics say cannot be built. Astronomers have desperately tried to find a loophole in the physics. If the star could not have formed through standard accretion, perhaps there is a mechanical explanation we have missed. Some suggest that perhaps we are not looking at a single star at all, but a tight binary system. Two stars orbiting so closely together that our current telescopes cannot resolve them. If R136a1 were actually two stars, each weighing 150 solar masses, the Eddington limit would be safe. The laws of physics would remain intact. But the data denies this comfort. We analyze the light using spectroscopy. We break the incoming light down into its component wavelengths. If there were two stars orbiting each other, their immense gravity would cause them to pull on one another. As they danced around their common center of mass, the light they emit would shift. As one star moved toward us, its light waves would compress, shifting slightly to the blue end of the spectrum. As it moved away, the light would stretch, shifting toward the red. This alternating redshift and blue shift is the signature of a binary system. We have looked for this signature in R136A1. We have measured its spectrum with absolute precision. The light does not shift. The signature is singular. The data is unyielding. There is only one source of gravity. It is a single, solitary core. If accretion is impossible, and it is not a binary system, there is only one other theoretical pathway: stellar cannibalism. Perhaps R136A1 did not form as a 300 solar mass giant. Perhaps it started as several smaller, stable stars, clustered tightly together in the chaotic heart of the Tarantula Nebula. Over time, the relentless drag of gravity forced their orbits to decay. They spiraled inward, tearing at each other's atmospheres until they collided and merged into a single monstrous entity. But even this explanation carries a heavy mathematical penalty. When two massive stars collide, it is not a gentle fusion. The kinetic energy released is apocalyptic. A significant percentage of their combined mass would be violently ejected into deep space. To end up with a single star weighing 300 solar masses, you would need two stars weighing perhaps 200 solar masses to collide. But that simply pushes the problem backward. How did those 200 solar mass stars form in the first place? They, too, violate the Eddington limit. You cannot solve a mathematical impossibility by dividing it into two slightly smaller impossibilities. The wall remains. The physics cannot be bypassed. This is why R136A1 terrifies astrophysicists. It is not just a heavy object. It is a crack in the foundation of our understanding. Every time we measure the expansion of the universe, every time we calculate the mass of distant galaxies, we rely on our understanding of stellar physics. We use stars as standard candles to illuminate the darkness. If we do not understand how stars form, if we do not understand the absolute limits of their mass, then our measurements of the deep cosmos are built on unstable ground. The existence of this single star suggests that our physics models are either incomplete or completely wrong. If the rules we use to build our reality can be broken by a single point of light in the Magellanic Cloud, we are forced to wonder what else is hiding in the dark. What other fundamental laws are waiting to be shattered? We are staring into an abyss that refuses to behave. And the deeper we look, the less we understand. If you seek the truth in the dark, if you want to explore the anomalies that break our understanding of reality, subscribe and join us on this journey. To comprehend the scale of this anomaly, you must first understand the immense difficulty of simply looking at it. The star R136A1 does not exist in our cosmic neighborhood. It is located 160,000 light-years away, well beyond the borders of the Milky Way, buried deep within the large Magellanic Cloud. The light entering our telescopes right now began its journey during the Middle Paleolithic era on Earth, long before human beings had even begun to form permanent settlements. For 160 millennia, those photons traveled through the absolute vacuum of intergalactic space, only to reach a tiny lens orbiting a pale blue planet. But crossing the void is the easiest part of the journey. The real barrier to understanding this star is the environment that surrounds it. R136A1 is hidden behind colossal walls of interstellar dust and cold gas. This is the Tarantula Nebula. It is the most active and complex region of star formation in our entire local group of galaxies. If this nebula were located where the Orion Nebula is, just 1,300 light-years from Earth, it would take up half of our night sky and cast visible shadows on the ground. It is a structure of staggering, incomprehensible size. And at its very center lies the R136 star cluster. This is not a normal stellar neighborhood. In the region of space surrounding our solar system, stars are separated by vast, empty distances. The closest star to our Sun is over 4 light-years away. It is a quiet, isolated existence. But the R136 cluster is a violent gravitational trap. In a sphere of space only a few light-years across, there are more than 100,000 stars tightly packed together. The physical crowding is extreme. If Earth were placed in the middle of this cluster, the concept of night would cease to exist. The sky would be entirely saturated with the blinding, overlapping glare of thousands of massive blue and white suns. The ambient radiation would be so intense that our oceans would immediately flash boil into the atmosphere, and the atmosphere itself would be stripped away into space by the sheer kinetic force of the surrounding starlight. It is an environment completely hostile to the delicate chemistry of life. And yet, even in this blinding crowd of giants, R136A1 dominates everything around it. When we say this star is over 300 times the mass of the Sun, it is easy to mistakenly imagine a sphere 300 times wider. But mass does not dictate physical volume in a simple, linear way. Gravity forces matter to compress. R136A1 is only about 30 to 40 times wider than our Sun. This means the density and the internal pressure of this object are pushed to the absolute extremes of physics. To understand the mechanics of this beast, you have to look past the blinding surface and examine its internal engine. Deep within the core, the crushing weight of 300 solar masses generates a physical pressure that defies human imagination. Under this pressure, the temperature at the center of the star spikes to tens of millions of degrees. Our own Sun generates energy through a relatively slow, inefficient process. It essentially forces individual hydrogen protons together to build helium. It is a quiet, steady burn. But the extreme temperature inside R136A1 unlocks a completely different nuclear mechanism. It is called the CNO cycle. Instead of merely smashing protons together, the core uses trace amounts of carbon, nitrogen, and oxygen as an industrial catalyst. A carbon nucleus captures a proton, mutates into nitrogen, captures another, mutates into oxygen, decays, and eventually spits out a fully formed helium nucleus while reverting back to carbon to start the process over again. It is a relentless, cyclical assembly line for nuclear detonation. Because this cycle is highly sensitive to temperature, the extreme heat of R136A1 causes the nuclear reactions to run at a terrifying speed. The core is not just burning fuel, it is actively detonating in a sustained, controlled fusion explosion that outputs nearly 9 million times the energy of our Sun. To put that into a concrete perspective, the total amount of energy that the Earth receives from the Sun over the course of an entire year is emitted by R136A1 in a fraction of a single millisecond. But this colossal energy output creates a secondary mechanical problem. How does the star transport all of that violent heat from the core to the surface? In smaller stars like our Sun, the interior is layered. The core produces heat, and the surrounding layers act as a dense, insulating blanket. The energy slowly radiates outward, photon by photon, taking hundreds of thousands of years to reach the surface. But the sheer volume of energy produced inside R136A1 cannot be contained by radiation alone. The core is too hot. The energy builds up too fast. As a result, the entire internal structure of the star physically boils. Physicists call this convection. Imagine a pot of boiling water where the hottest liquid rises to the top, cools slightly, and sinks back down to be heated again. Now scale that up to a sphere millions of miles wide, composed of superheated plasma. From the deepest core all the way to the outer atmosphere, the star is a churning, violent storm of convection currents. This boiling action has a massive consequence for the lifespan of the star. In a normal star, once the core runs out of hydrogen, the fusion stops, even if there is still plenty of hydrogen in the outer layers. The core is isolated, But because R136A1 is completely convective, it is constantly dredging up fresh hydrogen from its surface and dragging it directly down into the nuclear furnace while pulling the heavy helium ash upward. The star is actively feeding itself its own outer layers. It is eating its entire mass, ensuring that it burns as fast and as brightly as physically possible. We know all of this not because we can send a probe to the star, but because we can read the fingerprints it leaves in the light. Measuring the mass of something 160,000 light-years away requires a rigorous chain of logical deduction. We cannot simply put R136A1 on a scale. Instead, astronomers rely on the Space Telescope Imaging Spectrograph, an instrument aboard the Hubble Space Telescope. When Hubble looks at this star, it does not just take a photograph. The spectrograph takes the incoming light and shatters it, splitting it into a highly detailed spectrum. It looks for specific missing frequencies of light. When the intense extreme ultraviolet radiation leaves the surface of the star, it has to pass through the star's own outer atmosphere. This atmosphere contains heavy elements like ionized iron and nitrogen. These atoms act like a microscopic obstacle course for the light. When a photon of ultraviolet light hits an iron atom, the atom absorbs it. But more importantly, the atom absorbs the photon's kinetic momentum. Because the core is producing so many photons, this creates a continuous physical upward push on the heavy elements in the atmosphere. The iron atoms act like a parachute caught in a hurricane of light. They are physically lifted and blown away from the star, dragging hydrogen and helium along with them. This is the mechanism behind the star's catastrophic stellar wind. By looking at the spectrum of light, astronomers can measure the exact velocity of this wind. The data shows that the material is being blasted away from the star at over 2,600 kilometers per second. This number is the key to everything. To launch physical matter into space at that specific speed, the radiation pressure must be overcoming a very specific amount of gravity. If you know the velocity of the wind, you can calculate the escape velocity of the star. If you know the escape velocity and the radius, the laws of gravity allow you to calculate the exact mass of the object pulling inward. It is a flawless mathematical chain. The wind speed proves the gravity. The gravity proves the mass. The mass confirms the impossible. The result of this violent wind is that R136A1 is carving a massive hollow cavity into the Tarantula Nebula. The kinetic energy of the ejected material is slamming into the surrounding cold gas, creating cosmic shockwaves that echo for dozens of light-years. The extreme ultraviolet radiation is sterilizing the space around it, instantly destroying the complex molecules necessary for any planetary formation. It is a paradox of creation and destruction. The sheer gravity of the nebula allowed this monster to be born, and now the monster is systematically dismantling the nebula from the inside out. But as astronomers mapped the mechanics of its wind and the temperature of its boiling core, they realized that the true horror of R136A1 is not what it is doing to the space around it. The true horror lies in what is destined to happen inside its core. Because it is burning so violently, and because it possesses a mass that defies the fundamental limits of stability, this star is accelerating toward an evolutionary dead end. It is too massive to die quietly, and it is too massive to die in a standard supernova. The physics governing its internal structure dictate that when the nuclear fuel finally runs out, the resulting collapse will trigger a phenomenon so violent it threatens to erase the star entirely. To understand the theoretical impasse we have reached with this star, we have to look at how the machinery of the universe breaks down at extreme scales. The physics governing the life and death of a star is essentially a study of thermodynamic architecture. A star is a structure built to hold up its own weight. In a normal stellar body, this architecture is highly stable. As the core fuses hydrogen into helium, the energy released creates outward pressure. When the hydrogen runs out, the core contracts, the temperature spikes, and the star simply switches to fusing the helium into carbon. It is a reliable, predictable engine. But R136A1 is not a normal star. Its mass is so extreme that it has fundamentally altered the rules of its own internal thermodynamics. Because the gravitational weight crushing down on the core is so immense, the star cannot afford to burn its fuel slowly. It is forced to run its nuclear reactor at a catastrophic pace just to maintain its structural integrity, and this creates a severe problem with the timeline of its life. Every time the core depletes a fuel source and moves to the next heaviest element, the reaction becomes vastly less efficient. The core must contract and heat up to an even higher temperature to ignite the next fuel, and because it is hotter, it burns through that new fuel exponentially faster. It is a runaway cycle of diminishing returns. We can map this acceleration mathematically. For a massive star, the hydrogen burning phase might last a few million years. When the hydrogen is exhausted, the core shrinks and the temperature reaches hundreds of millions of degrees to ignite helium. The helium phase might last only a few 100,000 years. Then the helium runs out. The core contracts again. The temperature rises to over 500 million degrees, and the star begins fusing carbon into neon. The carbon supply will be completely exhausted in perhaps a few hundred years. From this point, the timeline collapses entirely. The core reaches over 1 billion degrees to fuse neon into oxygen, a phase that lasts only about a year. Then the oxygen ignites, fusing into silicon. This process takes only a few months. And finally, the core reaches a staggering 3 billion degrees, and the silicon begins fusing into iron. For a massive star, the entire supply of silicon in the core will be consumed in less than a single day. The star has spent millions of years building up to this moment, but the final desperate struggle to hold up its own mass happens in a matter of hours. And when the core turns to iron, the thermodynamic engine hits a brick wall. Iron is the most tightly bound nucleus in the universe. Up to this point, every time the star fused lighter elements into heavier ones, the reaction released energy. That energy provided the kinetic push to hold the star up. But fusing iron requires more energy than it releases. It is an energy sink. Instead of generating the outward pressure needed to fight gravity, iron actively absorbs it. The moment the core becomes primarily iron, the nuclear fire that has sustained the star for millions of years simply goes out. Gravity instantly wins the war. In a standard massive star, perhaps 20 or 30 times the weight of our Sun, this sudden loss of pressure causes the core to collapse in on itself. The outer layers of the star fall inward at a significant fraction of the speed of light, slam into the ultra-dense iron core, and bounce outward in a colossal shockwave. This is a standard supernova. The outer layers are blasted into space, and the crushed core remains behind as a neutron star or a small black hole. But R136A1 is over 300 solar masses, and at this extreme scale, the standard models of physics stop working. The star is so heavy and its core is so unimaginably hot that it triggers a quantum mechanical anomaly long before it ever reaches the iron phase. It is a phenomenon known as pair instability. To understand this theoretical barrier, you have to look at the exact nature of the light holding the star up. Inside the core of R136A1, the temperature is so high that the photons being generated are not visible light or even standard X-rays. They are highly energetic gamma rays. These gamma ray photons possess a massive amount of kinetic momentum, and they are the only thing providing the outward pressure against the crushing weight of 300 suns. But as the core heats up during the final stages of its life, these gamma rays become increasingly energetic. Eventually, they reach a very specific critical energy threshold. According to the equations of quantum mechanics, when a photon is this energetic, it can interact with the nucleus of an atom and spontaneously vanish. The energy of the light is converted directly into physical mass. The photon transforms into two particles, an electron and its antimatter twin, a positron. This is the exact reverse of a nuclear bomb. Instead of matter turning into energy, the energy of the star is suddenly turning into matter. This transformation causes a catastrophic structural failure. Photons exert outward radiation pressure. Electrons and positrons do not. The moment the gamma rays begin turning into matter, The immense kinetic pressure holding the star up simply disappears. It is as if the steel pillars supporting a massive skyscraper suddenly turned into dust. With the internal pressure gone, the outer layers of the star are no longer in equilibrium. Hundreds of solar masses of superheated plasma suddenly go into freefall. The star collapses inward at terrifying speeds. As all this mass crashes down into the core, the temperature and pressure spike to levels that break the boundaries of conventional fluid dynamics. The sudden, violent compression forces all the remaining oxygen and silicon in the star to ignite at the exact same instant. The result is a runaway thermonuclear explosion of incomprehensible scale. Physicists call this a pair instability supernova. In a normal supernova, the core survives as a dense remnant, but the thermonuclear detonation triggered by pair instability is so absolute, so overwhelmingly violent, that the gravitational binding energy of the star is completely overcome. The explosion literally unbinds every single atom of the star. It leaves nothing behind. No black hole, no neutron star. The entire 300 solar mass object is entirely obliterated, scattering hundreds of thousands of Earth masses of newly forged, highly radioactive heavy elements into the void. It is the complete unmaking of a star. For decades, astrophysicists believed this was the inevitable violent fate of any star massive enough to violate the Eddington Limit. Our computer models dictated that pair instability was the ultimate executioner of supermassive stars, but as we improved our measurements of R136A1, the data revealed a new and deeply frustrating complication. The star might actually be too massive to explode. When astrophysicists feed the parameters of a 300 solar mass object into supercomputer simulations, the physics cross yet another threshold. The core temperature becomes so extreme that the gamma rays bypass the pair instability phase entirely. Instead of just turning into electrons and positrons, the gamma rays become so violently energetic that they act like physical hammers. They begin smashing into the heavy nuclei in the core, physically shattering the atoms back into lighter elements like helium and free protons. This process is known as photodisintegration. This creates an even more absolute thermodynamic crisis. Shattering atomic nuclei requires a massive amount of energy. The gamma rays literally suck all the thermal energy out of the core to break the atoms apart. The temperature plummets. The pressure drops to zero instantly. In this scenario, the collapse is so fast and the mass falling inward is so immense that the resulting shockwave cannot escape. The gravity of the collapsing star overwhelms the force of the thermonuclear explosion. The density at the very center reaches infinity, tearing a hole in the fabric of space-time. An event horizon forms from the inside out. Instead of blowing itself to pieces in the brightest explosion in the universe, the star simply swallows itself. Hundreds of solar masses of material fall straight into a newly born black hole in a matter of seconds. From the outside, there is no supernova. There is no brilliant flash of light. To an observer, this colossal dominating giant would simply blink out of existence, leaving behind a dark, silent tear in the gravitational field of the Tarantula Nebula. This is the barrier we have hit. We are observing an object that stands on the razor's edge of completely opposing physical models. We have the pair instability model, which predicts a total unrecoverable explosion. And we have the direct collapse model, which predicts a silent vanishing. The frustration among astrophysicists is palpable. Science relies on predictive modeling. If you know the starting conditions of a physical system, the equations should tell you exactly how that system will end. But when we apply our best equations of hydrodynamics, nuclear physics, and general relativity to R136A1, the math begins to break. The formulas yield contradictory results. The extreme radiation pressure creates chaotic turbulence in the computer models, causing the simulations to crash. We lack the mathematical vocabulary to properly describe what is happening inside the core of this object. And this leads us to the ultimate paradox of the star. We are trying to predict the death of an object using the exact same physical models that say it should never have been born. We rely on the Eddington limit to understand radiation pressure, yet R136A1 openly violates the Eddington limit every single second it exists. We rely on standard accretion models to explain how stars gather mass, yet those models prove that gathering 300 solar masses is mechanically impossible. If our fundamental equations for stellar formation are wrong, then our equations for stellar death are built on a fractured foundation. We are attempting to forecast the behavior of an anomaly using the very rules the anomaly is currently breaking. The barrier is not just distance. The barrier is the limit of human physics. We are looking at a machine operating in the deep universe, and we are forced to admit that we do not have the blueprint. We know the mass, we know the temperature, we know the violent velocity of the stellar wind, but the internal mechanism holding it all together remains entirely hidden from us. We are left with an uncomfortable reality. The universe allows for structures that our current mathematics simply cannot tolerate. And as we continue to study the violent radiation pouring out of this impossible star, we have to confront what its existence means for the rest of the cosmos. If stars this massive can form, and if they can die without leaving a trace, they are quietly shaping the evolution of galaxies in ways we have not even begun to calculate. The existence of this star is not an isolated glitch in an otherwise perfect universe. It is a fundamental warning. When we find an object that operates completely outside the established laws of physics, the implications do not stay confined to a single nebula. The mechanics that govern a 300 solar mass star have cascading, violently disruptive effects on the structure of the cosmos. The anomaly of R136a1 forces us to reconsider the ultimate fate of galaxies, the origin of the elements that build planets, and the very fabric of space-time itself. To understand the true scale of the consequences, we must first look at the cosmic economy of chemical elements. The universe was born in a state of extreme simplicity. Following the Big Bang, the cosmos contained almost nothing but hydrogen, a smaller amount of helium, and microscopic traces of lithium. That was the entire periodic table. There was no carbon, no oxygen, no silicon, no iron. The early universe was completely incapable of forming solid planets, let alone biological life. Every single atom heavier than helium had to be manufactured inside the nuclear furnace of a star, and then violently expelled into the void through a supernova explosion. Astrophysicists call this process chemical enrichment. It is a slow, agonizingly inefficient industrial process. A normal star, like our Sun, will eventually manufacture carbon and oxygen, but it will never explode. When it dies, it will simply lock those heavier elements inside a dense, dead core known as a white dwarf. The vast majority of the heavy elements that make up the Earth, the iron in human blood and the calcium in human bones, were forged in the cores of massive stars that blew themselves apart in the distant past. This is where the mathematical nightmare of R136a1 becomes highly relevant to our own existence. Supermassive stars are the primary engines of chemical enrichment. Because they burn so violently and process so much material, they are the heavy industry of the universe. If the pair instability supernova model is correct, and a star like R136a1 eventually detonates completely, the sheer volume of heavy elements it injects into the surrounding galaxy is staggering. A single explosion of this magnitude would flood the Large Magellanic Cloud with enough newly forged iron, carbon, and oxygen to build millions of terrestrial planets. It would function as a massive seed of creation, fertilizing the cold gas clouds for future generations of solar systems. But as we have seen, the physics suggest this explosion might not happen. If the alternative model is correct, and the extreme mass of R136a1 causes it to undergo photodisintegration and collapse directly into a black hole, the consequences are entirely different. Instead of scattering its heavy elements into the void, the star swallows them. Hundreds of solar masses of carbon, silicon, and iron are permanently deleted from the observable universe. They cross the event horizon and are locked away forever, completely useless to the future of the galaxy. This creates a terrifying statistical problem for the formation of planetary systems. If the most massive stars in the universe routinely collapse directly into black holes without exploding, then the cosmic factories producing the raw materials for terrestrial planets are routinely shutting down and burying their own products. It means the universe is far less efficient at building solid worlds than we thought. The chemical lottery that allowed the Earth to form required a very specific sequence of stellar deaths, and the existence of direct collapse black holes implies that the conditions for building habitable worlds are far more constrained and precarious than our current models suggest. But the influence of this giant extends far beyond the chemical makeup of future planets. While it is still alive, R136a1 is acting as an active sterilizer. We tend to think of star formation as an unstoppable natural process. As long as there is gas and dust, gravity will pull it together and ignite new suns. But star formation requires a very specific thermodynamic condition. The gas must be incredibly cold. When hydrogen gas is cold, it is dense, and gravity can easily grip it and force it to collapse. If the gas heats up, the kinetic energy of the atoms causes them to move faster. They push away from each other. The cloud expands and gravity loses its grip. The extreme ultraviolet radiation pouring out of R136a1 is not just bright, it is kinetically destructive. When this high-energy radiation strikes the surrounding cold hydrogen in the Tarantula Nebula, it does not just warm it up. It triggers a violent process called ionization. An atom of hydrogen consists of a single proton orbited by a single electron. When a powerful ultraviolet photon hits that atom, it transfers all of its momentum to the electron. The impact is so violent that the electron is physically kicked out of its orbit and sent flying into space. The gas is stripped of its electrons, transforming from cold neutral hydrogen into a superheated electrically charged plasma. This plasma reaches temperatures of tens of thousands of degrees. At this temperature, the gas cloud expands explosively. It creates a high-pressure bubble that pushes outward against the rest of the nebula at supersonic speeds. This is the hidden violence of R136a1. Its light is physically heating and shredding the cold gas clouds for dozens of light years in every direction. By keeping the gas superheated and ionized, the star is actively preventing gravity from forming any new stars in its vicinity. It is aborting thousands of potential solar systems before they can even begin to collapse. Astrophysicists call this process galactic quenching. Galaxies are not passive collections of stars, they are dynamic machines governed by feedback loops. Gas cools down, and a cluster of stars is born. The most massive stars in that cluster immediately begin pumping out lethal radiation and violent stellar winds, heating the gas back up and shutting down any further star formation. The galaxy regulates itself. But a star of 300 solar masses exerts a level of feedback that completely breaks this local thermostat. It is a mechanism of absolute cosmic suppression. A single, impossible anomaly dictates the fate of millions of potential stars. It forces us to realize that the architecture of a galaxy is not shaped purely by the slow, gentle pull of gravity over billions of years, but by the brief, catastrophic violence of a few hypermassive giants that refuse to play by the rules. And this violence leaves scars that ripple through the fundamental fabric of reality. If we assume the direct collapse scenario is true and R136a1 is destined to vanish into a black hole, it forces us to confront a recent and profound discovery in observational astrophysics. For decades, Albert Einstein's theory of general relativity predicted the existence of gravitational waves. Einstein argued that space and time are not an empty stage, but a physical fabric. If you accelerate a massive object, it should create ripples in that fabric, exactly like a stone thrown into a quiet pond. For a century, this was purely theoretical. The ripples would be so incredibly microscopic by the time they reached Earth that measuring them seemed mechanically impossible. But in recent years, instruments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, finally achieved the impossible. Using laser beams traveling down vacuum tubes several kilometers long, physicists measured changes in the distance between mirrors that were smaller than the width of a single proton. They detected the ripples in space-time, But what they heard completely shattered our understanding of stellar death. LIGO detected the collision and merger of black holes. As two black holes spiral toward each other, they churn the fabric of space-time, radiating kinetic energy in the form of gravitational waves until they finally slam together. By analyzing the frequency and amplitude of these invisible ripples, physicists can calculate the exact mass of the black holes that collided. According to standard models of stellar evolution, the heaviest black hole a dying star should be able to produce is roughly 40 to 50 times the mass of our Sun. Anything heavier than that should be destroyed entirely by a pair instability supernova. The models dictated a strict gap in the mass of black holes. You can have small ones, and you can have supermassive ones in the center of galaxies, but nothing in the middle. But the ripples detected by LIGO told a different story. The data showed collisions between black holes weighing 60, 80, and even over 100 solar masses. These objects are known as intermediate mass black holes, and they are mathematical ghosts. They exist exactly in the mass gap where our equations say nothing should survive. Their existence proved that the universe possesses a mechanism for building colossal black holes that bypass the supernova phase entirely. The discovery of R136A1 provides the terrifying solution to this mystery. If stars weighing 300 solar masses can somehow form despite the extreme radiation pressure, and if they collapse directly into the dark without exploding, they would leave behind exactly the kind of massive black holes that LIGO is hearing. R136A1 is the physical proof that the universe can manufacture the impossible components required to tear the fabric of space-time. Every time LIGO detects one of these massive collisions, we are essentially hearing the final echo of a star that defied the Eddington Limit millions of years ago. It means that objects like R136A1, despite being incredibly rare, are the architects of the most violent gravitational events in the observable universe. They are the invisible anchors altering the trajectory of entire star clusters. But the existence of this star also threatens our understanding of cosmic time. When we look at the evolution of the universe, there is a strict chronological order. Shortly after the Big Bang, the universe contained no heavy elements. Because there was no carbon or oxygen to help cool the collapsing gas clouds, the very first stars to form were forced to be massive. Astronomers call this hypothetical first-generation population 3 stars. The math suggests they were absolute monsters, weighing hundreds of solar masses, burning furiously and dying in rapid succession. They were the primordial engines that seeded the early cosmos. But as the universe aged, and space became polluted with the heavy elements expelled by these first stars, the dynamics of star formation changed. Heavy elements allow gas clouds to cool much faster, and cooler clouds fragment into smaller pieces before they collapse. Because of this chemical pollution, the modern universe is heavily biased toward creating small, low-mass stars like our Sun. The era of the hypermassive titans should have ended billions of years ago. Yet here is R136A1, sitting in a satellite galaxy right next door to the Milky Way. It is a relic of the early cosmos, operating in the modern era. The large Magellanic Cloud has a lower concentration of heavy elements than the Milky Way, but it is not entirely pristine. It is not the early universe. The fact that a star of this magnitude could form in a modern, chemically enriched environment proves that the timeline of stellar evolution is not a smooth, predictable decay. The universe is still capable of generating apocalyptic conditions locally. It proves that the violent, extreme mechanics of the early cosmos can be abruptly resurrected if a gas cloud reaches sufficient density. It is a chronological anomaly, a ghost of the Big Bang burning in our immediate cosmic neighborhood. This chronological disruption leads to the most dangerous consequence of all. It is an epistemological threat. It challenges how we know what we know. Virtually everything we understand about the scale, age, and expansion of the universe is built on a very specific set of assumptions about how stars work. To measure the distance to galaxies billions of light-years away, astrophysicists use objects known as standard candles. These are usually Type Ia supernovae or pulsating stars called Cepheid variables. Because we believe we understand the exact physics of how these objects burn and explode, we believe we know their true intrinsic brightness. By comparing their true brightness to how dim they appear in our telescopes, we calculate the distance. It is the fundamental yardstick of cosmology. This yardstick is what allowed us to discover that the expansion of the universe is accelerating. It is the foundation for the concept of dark energy. But this entire structure relies on the absolute reliability of our stellar models. If the fundamental equations governing radiation pressure, accretion, and stellar mass limits are broken by objects like R136A1, the yardstick itself comes into question. If the extreme stellar winds and radiation environments created by these hypermassive giants are altering the behavior of the smaller stars around them, they could be skewing the luminosity of our standard candles. We are measuring the architecture of the cosmos using rulers built from our understanding of local physics. But R136A1 is a screaming alarm that our local physics models are incomplete. If the internal thermodynamic engine of a star can scale up to 300 solar masses without blowing itself apart, there are entire chapters of nuclear physics and fluid dynamics that we have yet to write. We are standing on the shore of a vast, dark ocean, assuming that the waves in the deep operate by the same rules as the ripples at our feet. R136A1 is the shadow of a leviathan that proves our math is limited. It forces us to accept a deeply uncomfortable truth about our place in reality. The universe is not a perfectly tuned machine designed to be neatly decoded by human mathematics. It is a violent, chaotic expanse that routinely builds structures that should not exist, operating on mechanics that remain locked in the dark. Every time we point our telescopes at the Tarantula Nebula, we are forced to observe a phenomenon that actively resists human logic. It is a brilliant, blinding reminder of the limits of our intelligence and the terrifying scale of what we do not yet understand. Human beings have an absolute, desperate need for order. We cannot tolerate chaos. When we look up at the chaotic spread of stars in the night sky, we immediately try to draw lines between them. We invent constellations, we invent myths, and as we grew more advanced, we replaced those myths with mathematics. We built complex physics models, elegant equations, and rigid laws of thermodynamics. We did this because if the universe can be calculated, it can be understood, and if it can be understood, it feels less terrifying. Mathematics gave us the illusion that we had somehow tamed the dark. But mathematics is ultimately just a human language. It is a framework we invented to describe the reality we see from a very specific, very safe vantage point. Our entire perspective on the cosmos is biased by the extreme safety of our own environment. We live on a quiet rock, orbiting a quiet, unremarkable yellow dwarf star. It is a stable system. It operates on gentle, predictable mechanics. Because we evolved in this calm, low-energy pocket of space, we naturally assume that the rest of the universe must follow the same sensible rules. We assume that stability is the default state of reality. R136A1 is the physical proof that our neighborhood is a statistical illusion. The true nature of the cosmos is not quiet. It is a state of relentless, uncontainable violence. And when we confront an object that embodies that violence, our human language of mathematics begins to break. When an object contains the mass of 300 suns, it stops being just a celestial body. It becomes a monument to our own epistemological limits. We have pointed our most advanced instruments at it. We have measured its heat, its extreme ultraviolet radiation, its catastrophic stellar wind, and its staggering gravitational pull. We possess all the raw data, yet the data refuses to fit into the framework of human logic. The star stands in absolute defiance of the very equations we use to discover it. This is the most deeply unsettling realization in modern astrophysics. The universe is under no obligation to make sense to us. We often treat science as a final destination. We carry this arrogant assumption that human intelligence is the ultimate tool for decoding reality. We believe that if we just build a larger telescope or write a more complex algorithm, or run a longer computer simulation, we will eventually uncover the complete machinery of existence. We assume that the laws of physics we discovered on Earth are universal laws. We assume that if a rule works here, it must work everywhere. R136A1 violently dismantles that arrogance. It proves that what we call the fundamental laws of physics might just be local guidelines. They are the rules that apply only in the cold, calm, low-energy environments where fragile things like biology are allowed to exist. But out there, in the extreme density of a supercluster, under the crushing kinetic pressure of millions of degrees, those local guidelines disintegrate entirely. The universe operates on a completely different set of mechanics when it is pushed to the absolute extreme. And this forces us to ask a terrifying question. How many other local guidelines are we mistaking for universal truths? If the physical rules governing stellar mass can be bypassed so effortlessly, what about the rules governing time? What about the rules governing the expansion of the void? We are trying to map an infinite hostile ocean using the logic of a single drop of water. The existence of this giant suggests that human intelligence might have a hard biological limit. Just as a dog cannot comprehend the engineering of a combustion engine, no matter how long it looks at it, there may be physical mechanics operating in the deep universe that the human brain simply does not have the architectural capacity to understand. We might be fundamentally incapable of grasping the whole picture. We are trying to read a book where half the pages are missing, and the other half are written in a language that our minds cannot translate. And while we struggle to reconcile our broken models, the monster in the Tarantula Nebula simply continues to burn. It does not wait for us to understand it. It sits there in the dark, pouring out lethal radiation, stripping its own mass away, and accelerating toward a violently uncertain end. In a few million years, which is less than a fraction of a second on the cosmic clock, it will reach the end of its impossible life. It will either detonate with enough force to outshine an entire galaxy, scattering newly forged elements into the void, or the internal pressure will fail, and it will collapse silently into a black hole, erasing hundreds of solar masses from the observable universe in a single silent heartbeat. It will do this with absolute indifference to whether we ever figured out how it worked. The anomaly in the Large Magellanic Cloud offers no comfort. It offers no deeper meaning. It offers only a cold mechanical reality. The cosmos was not built for us. It was not designed to be decoded by us. It is a blind, churning engine of creation and destruction, operating on scales that render human existence mathematically irrelevant. We spend our brief lives worrying about human timelines, decades, centuries. We build monuments to ourselves, and we believe that our legacy matters. But 160,000 light-years away, there is a machine that sheds the mass of our entire planet every few days, and it does not even notice. It is a structure of such immense, unthinking power that its eventual death will tear a permanent hole in the fabric of space-time. When the end finally comes for R136A1, there will likely be no human observers left to record it. By the time the light of its final collapse crosses the intergalactic void and reaches the Earth, another 160,000 years will have passed. Our modern civilizations will be gone. Our languages will be forgotten. The telescopes we used to find this star will have crumbled into dust. The universe will simply move on. It will continue to build impossibilities in the dark, entirely indifferent to our absence. We are a brief, fragile spark of awareness, waking up for a fraction of a second to realize exactly how small we are before the dark takes over again.